It is late, and you have arrived here. Whether your day was kind or difficult, this hour is yours to rest. Let the small worries that climb into the dark slip back beneath the surface. Tonight we will drift very slowly into the deep, slow story of Saturn and its rings, the great pale gas giant of the outer solar system, surrounded by a luminous halo of ice and dust, attended by dozens of quiet moons in the patient cosmic dark. This is the Circadian Institute. We exist for the long nights, for the in-between hours when the body is ready to sleep, but the mind is still moving. Tonight, our subject is the deep, slow story of Saturn, the second largest planet in the solar system, with its famous golden bands of cloud, the brilliant ring system stretching across 280,000 kilometers of cosmic space, the strange hexagonal storm at its north pole, the haze-shrouded moon Titan with its lakes of liquid methane, the icy geyser moon Enceladus with its Hyperion, an ocean, and all of the gentle small worlds that orbit this distant, patient giant. If this kind of slow journey suits you, subscribing keeps these nights arriving. Tonight, we will travel together through the world of Saturn. We will visit the pale golden body of the planet itself, the strange hexagonal storm at its north pole, the brilliant ring system stretching far across cosmic space, the moon Titan with its lakes of liquid methane, the geyser moon Enceladus with its hidden ocean, and many of the smaller icy moons that keep Saturn quiet company through the long cosmic night. There is no hurry. We have all the time we need. To begin tonight's journey, we will visit Saturn itself. Saturn is the sixth planet from the Sun, and the second largest in our solar system. Only Jupiter exceeds it in size. Saturn is a gas giant, which means it has no solid surface. Beneath its outer layers of cloud lies a vast ocean of liquid hydrogen, and deeper still, a small dense core of rock and metal. Saturn orbits the Sun at an average distance of about 1.4 billion kilometers. That is more than 9 times the distance from Earth to the Sun. Light from the Sun takes nearly 80 minutes to reach Saturn. The Sun, seen from Saturn, would appear small but still very bright, about 100 times brighter than the full moon as seen from Earth. A single Saturn year, the time it takes Saturn to complete one orbit around the Sun, lasts about 29.5 Earth years. A child born when Saturn was in one part of the sky would be nearly 30 years old before Saturn returned to that same position. This long, quiet rhythm makes Saturn one of the slowest moving objects visible to the unaided human eye. In contrast to its slow orbit, Saturn rotates on its axis very quickly. A single Saturn day lasts only about 10.5 Earth hours. The planet is so large that this rapid rotation actually flattens it slightly. Saturn is noticeably more oblate than any other planet in the solar system, bulging at its equator by about 10%. Saturn is enormous. It is about 9.5 times wider than Earth, which means more than 750 Earth-sized planets could fit inside it. Yet despite its size, Saturn is remarkably light. Its overall density is lower than that of water. If you could find a bathtub large enough, Saturn would actually float. The pale golden color of Saturn comes from its outer cloud layers. These clouds are made of crystals of ammonia, which scatter sunlight in a soft, warm hue. Beneath these visible clouds are deeper layers of ammonium hydrosulfide and water clouds that human eyes have never directly seen. Saturn's atmosphere goes deeper than any solid feature on Earth. The cloud bands of Saturn run roughly parallel to its equator, much like the cloud bands of Jupiter. But Saturn's bands are softer, less colorful, less sharply defined. The hazy upper atmosphere blurs the deeper detail, making Saturn appear almost like a softly painted globe. Astronomers have spent centuries studying these gentle bands and watching them slowly change. Saturn was first observed through a telescope by the Italian astronomer Galileo Galilei in 1610. Galileo could see that Saturn was not a simple round disk like the other planets around it, were strange shapes that he could not quite resolve with his small telescope. He famously described Saturn as a planet with handles, or as a planet made of three bodies side by side. It was the Dutch astronomer Cassini-Huygens, with a better telescope, who in 1659 correctly identified the strange shapes as a flat ring system surrounding Saturn. The discovery of Saturn's rings was one of the great revelations of early modern astronomy. Nothing else in the known universe at that time looked anything like it. Saturn's mass is about 95 times that of Earth, but only about 30% the mass of Jupiter. Like Jupiter, Saturn is composed mostly of hydrogen and helium. There is no clear boundary between Saturn's atmosphere and its deeper interior. The gases simply grow thicker and thicker under increasing pressure, gradually turning into liquid hydrogen far below the visible clouds. Deep inside Saturn, at pressures hundreds of thousands of times greater than Earth's atmosphere, hydrogen takes on a strange form. The atoms are squeezed so tightly that the electrons no longer remain bound to individual nuclei. The hydrogen becomes a metallic conducting fluid. This vast inner ocean of metallic hydrogen is the source of Saturn's powerful magnetic field. At the very center of Saturn lies a small, dense core of rock and ice, perhaps 10 or 15 times the mass of Earth. The temperature at the core is estimated to be around 11,000 degrees Celsius, hotter than the surface of the Sun. Yet because the immense pressure keeps the material from glowing visibly, Saturn appears cool and pale from the outside. Saturn emits more energy than it receives from the Sun. The slow ongoing settlement of helium droplets falling through its liquid hydrogen interior releases gravitational energy as heat. This internal heat source warms the planet from within and helps drive the gentle weather patterns visible in its outer atmosphere. Saturn has been visited by spacecraft only 4 times in human history. The first was Pioneer 11 in 1979, followed by Voyager 1 in 1980 and Voyager 2 in 1981. The most extensive mission was Cassini-Huygens, which orbited Saturn for 13 years between 2004 and 2017. Together, these missions have revealed most of what we know about Saturn today. From Earth, Saturn can be seen with the unaided eye on most clear nights when it is positioned away from the Sun. It appears as a steady yellow point of light, distinguishable from a true star by its non-twinkling quality. Through even a small backyard telescope, the rings become visible. For many people, the first sight of Saturn's rings through a telescope is a moment they remember for the rest of their lives. Tonight, Saturn continues its slow orbital journey around the Sun. The clouds drift, the rings turn, the moons follow their long, quiet paths. Saturn has been doing this for 4.5 billion years, since the early formation of the solar system. It will continue for billions more, long after every memory of human civilization has faded. Now, gently, We will look more closely at the atmosphere of Saturn, at the soft cloud bands that wrap around the planet and the slow, gentle storms that move within them. Saturn's atmosphere is composed primarily of hydrogen and helium, with smaller amounts of methane, ammonia, water vapor, and various trace gases. By mass, hydrogen makes up about 96% of the atmosphere, helium makes up about 3%, and the remaining 1% contains all of the other gases that give Saturn its characteristic color and weather. The visible cloud bands of Saturn are formed at different altitudes and contain different chemicals. The uppermost layer, which we see from space, is composed of fine ammonia ice crystals. These crystals scatter sunlight in a soft, pale yellow color, giving Saturn its characteristic golden appearance. Below this layer are deeper clouds of ammonium hydrosulfide and water. Saturn's cloud bands run parallel to the equator, just like Jupiter's. The lighter colored bands are called zones, and the darker bands are called belts. Within each zone or belt, winds blow either eastward or westward at high speeds. The contrast between adjacent bands creates the slow patterned appearance that we see from above. The winds on Saturn are among the fastest in the solar system. At the equator, wind speeds can reach over 1,800 kilometers per hour, faster than the speed of sound on Earth. These powerful jet streams have been blowing in the same general direction for as long as humans have been able to observe them, and probably for much longer. Despite the powerful winds, Saturn's atmosphere appears strangely calm and uniform compared to Jupiter's. There are fewer dramatic storms, fewer visible swirls, fewer sharp color boundaries. This is partly because Saturn is farther from the Sun and receives less heat, slowing the chemistry that would normally produce vivid colors. The hazy upper atmosphere also blurs much of the deeper detail. Occasionally, however, Saturn does produce dramatic storms. About once every Saturn year, roughly every 30 Earth years, a great white storm appears suddenly in the northern hemisphere. The storm grows over weeks until it eventually wraps all the way around the planet, forming a bright white band visible from Earth. After several months, it fades back into the regular atmosphere. The most recent Great White Storm was observed in 2010 by the Cassini spacecraft. The storm was one of the largest ever recorded on Saturn, eventually stretching all the way around the planet. Cassini was perfectly positioned to study its development in unprecedented detail, capturing images and data that helped scientists understand how such storms form and dissipate. Lightning has been detected in Saturn's atmosphere. The lightning bolts on Saturn are about 10,000 times more powerful than typical lightning on Earth. They occur in storm cells deep within the cloud layers and emit radio waves that can be detected by spacecraft passing nearby. The Cassini mission detected radio bursts from Saturn's lightning many times during its long orbit. Saturn also produces aurora displays at its poles. Like Earth's auroras, these are caused by charged particles from the Sun spiraling down along magnetic field lines into the atmosphere. The auroras on Saturn glow softly in shades of blue and violet, and they form ring shapes around the magnetic poles. These polar light shows can persist for days at a time. The temperature in Saturn's outer atmosphere is very cold, around -180 degrees Celsius. As we move deeper into the planet, the temperature gradually increases, about 1,000 kilometers below the cloud tops. The temperature has risen to nearly 0 degrees. Much deeper still in the interior, Temperatures reach thousands of degrees. Saturn's clouds form distinct layers at different depths. The uppermost ammonia ice clouds are followed by ammonium hydrosulfide clouds about 150 kilometers below them. Below those are water clouds at depths of about 200 kilometers. Each cloud layer reflects sunlight in its own characteristic way, and together they create the soft, layered appearance of Saturn from space. Hubble Space Telescope observations and Cassini imagery have revealed that Saturn's cloud bands shift slightly over time. Some bands brighten or darken as decades pass. Storms come and go. The overall pattern is stable, but the details are constantly evolving. Astronomers can study these slow changes to learn about the deeper atmospheric dynamics that shape Saturn's weather. Recent observations from the James Webb Space Telescope have revealed new details about Saturn's atmosphere in infrared light. The thermal emission from Saturn's clouds shows patterns invisible in normal photographs, helping astronomers map the three-dimensional structure of the cloud layers and the temperature variations at different depths. Saturn's atmosphere extends far above the visible cloud tops. There is no clear boundary where the atmosphere ends and space begins. The outermost layers gradually thin into a tenuous exosphere that extends millions of kilometers from the planet. Some particles in this exosphere reach speeds high enough to escape Saturn's gravity entirely. In the upper atmosphere, ultraviolet sunlight breaks apart methane molecules, producing complex hydrocarbon compounds that drift down through the cloud layers. These compounds eventually condense into haze particles that contribute to the soft golden color of Saturn's appearance. The chemistry of this process is similar to the chemistry that creates Titan's thick orange haze. Saturn's atmosphere is also home to long-lived storm systems that can persist for years or even decades. One notable example is the Dragon Storm, a swirling pattern observed by Cassini in the southern hemisphere. The Dragon Storm was a continuous source of radio emissions and lightning, lasting throughout Cassini's mission and slowly evolving in shape and position. Now gently, we will turn to one of the strangest features in Saturn's atmosphere, the great hexagonal storm that sits in quiet permanence at Saturn's North Pole, a geometric pattern with no known equivalent anywhere else in the solar system. At Saturn's North Pole sits one of the most surprising features anywhere in the solar system, a vast cloud pattern shaped like a hexagon. The hexagon is enormous, measuring roughly 30,000 kilometers across, that is wide enough to fit nearly 4 Earth-sized planets across its diameter. The 6 straight sides and 6 sharp corners are visible in even modest telescope images. The hexagon was first noticed in Voyager spacecraft images from 1980 and 1981. At the time, it was so unusual that some astronomers thought it might be an artifact of the images themselves. But subsequent observations by other spacecraft and the Hubble Space Telescope confirmed that the hexagon was real and had persisted across decades of cosmic time. The Cassini spacecraft, in orbit around Saturn from 2004 to 2017, made the most detailed observations of the hexagon ever recorded. Cassini photographed the pattern from many angles and in many wavelengths of light, revealing the deep three-dimensional structure of the storm and its surrounding flows. The hexagon is actually a jet stream, a fast-moving river of air that flows around Saturn's North Pole. The straight sides of the hexagon are formed where the jet stream takes a relatively direct path. The corners are where the jet stream curves slightly. The whole pattern rotates very slowly compared to the underlying cloud layers below it. Inside the hexagon at the center is a great storm vortex that rotates rapidly. This vortex is sometimes called the eye of the hexagon. It has a deep blue or gray color in many Cassini images, contrasting with the surrounding paler clouds. The eye rotates much faster than the outer hexagonal jet stream, completing a turn in just hours. Why does Saturn have a hexagonal storm rather than a more typical round or oval pattern? Laboratory experiments and computer models suggest that the hexagonal shape can arise naturally when fluid flows around a sharp rotational axis. If the speed of the surrounding jet stream is just right, the natural meanders of the flow can lock into a six-sided pattern that is then maintained for a very long time. Each side of the hexagon is approximately 14,000 kilometers long. That is roughly the diameter of Earth. The winds along the hexagon's sides blow at about 350 kilometers per hour. These winds have been blowing in the same direction for at least 4 decades, and probably much longer. The hexagon has a strange relationship with the rest of Saturn's atmosphere. Below the hexagon, the underlying cloud layers rotate at slightly different rates than the hexagonal jet stream itself. This means that viewed from below, the hexagon appears to slowly drift over time, but viewed from above, in a fixed orientation, the hexagon is remarkably stable. Color images of the hexagon, processed from Cassini data, show beautiful blue and green shades inside the structure. The hexagon also appears to change color slightly over time as Saturn seasons progress. During Saturn's northern winter, when sunlight is scarce at the North Pole, the hexagon appears more blue. During northern summer, the colors shift toward yellow and gold. Saturn's south pole does not have a hexagonal pattern. Instead, the South Pole has a more typical circular polar vortex with a large eye-shaped storm at the center. The asymmetry between the North and South Poles is one of the most puzzling aspects of Saturn's weather. Astronomers are still working to understand why the two poles behave so differently. Computer simulations have shown that the hexagonal pattern is remarkably stable once it forms, even if the surrounding atmosphere is disturbed by storms or other events. The hexagon tends to reform back into its six-sided geometry. This stability is one of the reasons the hexagon has persisted for so long across decades of cosmic time. In late 2016, Cassini observed the hexagon from above for the first time when its orbit passed almost directly over Saturn's North Pole. The resulting images showed the hexagon in unprecedented detail. The straight sides were sharply defined, the corners were precisely angled, and the rapidly rotating central vortex was clearly visible. Saturn's hexagonal storm is one of the few features in the solar system that has no clear analog anywhere else. Jupiter has its great red spot, an enormous oval storm. Neptune has its dark spots. Earth has its hurricanes, but no other planet has a stable hexagonal pattern in its atmosphere. The shape remains uniquely Saturnian. Even though Cassini's mission ended in 2017, the hexagon continues. The James Webb Space Telescope has observed it in infrared light, and ground-based telescopes track its slow changes year by year. The hexagon is still there tonight, slowly rotating, 6 straight sides and 6 sharp corners, exactly as it has been since long before any human began watching it. Tonight, the hexagonal storm at Saturn's North Pole rotates quietly. The jet stream flows around its 6 sides. The central eye spins faster than the surrounding clouds. The pattern, beautiful and strange, persists in its cosmic stability, a reminder that even on the gentlest of gas giants, the natural laws of fluid dynamics can produce shapes more orderly than anything humans could design. The geometric perfection of Saturn's hexagon stands as a beautiful example of how natural patterns can emerge from simple physical laws acting over vast cosmic spaces and timescales. There is no hand of design at work here, only flowing fluid and conservation of momentum organizing themselves into one of the most surprising patterns in the universe. Now gently, we will turn from the strange hexagonal storm to the most famous feature of Saturn, the brilliant ring system that has fascinated human observers for nearly 4 centuries, ever since the rings were first correctly identified through a telescope. The rings of Saturn are one of the most beautiful sights in all of astronomy. They form a vast flat disk that extends from about 7,000 kilometers above the cloud tops of Saturn out to nearly 300,000 kilometers away. The total width of the main ring system is enormous, but the rings are extraordinarily thin, typically only about 10 meters thick. If Saturn's rings were scaled down so that the planet itself was the size of a basketball, the rings would extend out as wide as the height of an adult human standing nearby, but they would still be only about 1/10 of a millimeter thick, thinner than a sheet of paper. The extraordinary flatness of the rings is one of their most surprising features. The rings appear solid from a distance, but they are actually made of countless individual particles, each orbiting Saturn independently. These particles range from microscopic dust grains to chunks of ice the size of houses or even small mountains. The vast majority are pieces of water ice with smaller amounts of dust and other materials mixed in. The total mass of all the material in Saturn's rings is surprisingly small. If gathered together, it would form a single small moon roughly the size of Mimas, about 400 kilometers across. This is less than half the mass of Earth's moon. Despite their dramatic appearance, the rings contain only a tiny fraction of the material orbiting Saturn. Saturn's rings are usually divided into 7 major sections, labeled A through G in roughly the order they were discovered. The A ring is on the outside, followed by the famous Cassini division, a wide dark gap, and then the B ring. The C ring lies inside the B ring, even closer to the planet. The D ring is the innermost ring of all, very faint and close to Saturn's cloud tops. Outside the main ring system are the faint outer rings, the E, F, and G rings. The F ring is a narrow, bright band just outside the A ring, kept tightly contained by 2 small shepherd moons. The E ring is a very wide, diffuse cloud that extends far out to the orbit of the moon Enceladus, which feeds material into it. The brightness of Saturn's rings varies dramatically depending on which part you're looking at. The B ring is the brightest and densest, reflecting most of the sunlight that falls on it. The A ring is somewhat fainter. The C ring is much fainter still, often called the crepe ring because of its dark, gauzy appearance. The outer rings are extremely faint and require special imaging to see it all. From Earth, the rings of Saturn appear at different angles as the planet moves through its long orbit. Sometimes the rings are tilted so that we see them nearly face-on, with their full breadth visible. Other times the rings are nearly edge-on, and they almost disappear from view because they are so thin. This tilt cycle takes about 15 years to complete each way. The rings are perfectly aligned with Saturn's equatorial plane, which is tilted about 27 degrees from the plane of the solar system. This tilt is the reason why Saturn has seasons, similar to Earth's seasons, and why we see the rings at different angles during the course of Saturn's 29-year orbit. How did Saturn's rings form? Several theories have been proposed. One possibility is that the rings are debris from a moon that was torn apart by Saturn's gravity long ago. Another is that the rings are leftover material from the formation of Saturn itself, never gathered into a moon. A third possibility is that a comet was captured and shattered into the ring system. Recent data from Cassini suggests that Saturn's rings may be relatively young, perhaps only 100 million years old, far younger than Saturn itself. The rings are surprisingly clean of dark dust and meteoric material, which would have accumulated over longer time scales. This makes the timing of the rings' formation one of the great open questions in planetary science. Saturn's rings are also slowly disappearing. Tiny particles in the rings, especially those in the upper edges, are gradually being pulled into Saturn's atmosphere by gravity. Over millions of years, the entire ring system will eventually dissipate. Astronomers estimate that the rings may have only a few 100 million years left before they fade entirely. The rings are not static structures. They are constantly being disturbed by the gravitational influences of Saturn's many moons. Some moons orbit within the rings themselves, sweeping out clear gaps. Other moons orbit just outside the rings, creating waves and patterns in the ring material. Cassini's detailed imagery revealed many of these subtle features for the first time. When sunlight strikes the rings, it scatters in different directions depending on the size and composition of the particles. Smaller particles tend to scatter light strongly forward, while larger particles scatter it back. This means that the rings look very different from different viewing angles. From behind, the rings appear bright and luminous. From in front, they look more shadowed and structured. Cassini observed many shadow phenomena in the rings. The rings cast shadows on Saturn's cloud tops, creating dark bands across the planet. Saturn casts a shadow back across the rings on the side, away from the Sun. The interplay of light and shadow created some of the most beautiful images ever taken of any planet. Even from the surface of one of Saturn's moons, the rings would be a spectacular sight. From Mimas, for example, the rings would fill a large portion of the sky, glowing softly against the cosmic darkness. From Titan, the rings would appear as a thin, bright line across the haze. Each moon offers its own perspective on this great cosmic structure. Now gently, we will move closer to examine the main bright rings of Saturn, the A, B, and C rings, which together contain almost all of the ring system's visible material and brightness. The three main rings of Saturn are called the A, B, and C rings. They contain nearly all of the ring system's visible mass and brightness. Together, they extend from about 75,000 kilometers from Saturn's center out to about 140,000 kilometers. The rings were given letter names by early observers who labeled them in the order of discovery rather than in their spatial arrangement. The B ring is the brightest, densest, and most prominent of all of Saturn's rings. It is also the widest of the main rings, spanning about 25,000 kilometers from inner edge to outer edge. The B ring contains most of the total mass of the ring system. When viewed from Earth through even a small telescope, the B ring is the dominant feature visible. The B ring is so densely packed with particles that light cannot easily pass through it. From behind, the B ring appears as a dark band against the bright background of Saturn. Cassini observations revealed that the inner regions of the B ring contain particles tightly packed in patterns called self-gravity wakes, long parallel structures created by the mutual gravitational pull of nearby particles. The A ring lies outside the B ring, beyond the Cassini division gap. The A ring is somewhat fainter than the B ring, but still very prominent. It is also quite wide, spanning about 15,000 kilometers. The A ring is divided internally by another narrow gap called the Encke gap, which is partially cleared by the small moon Pan. The C ring lies closest to Saturn's cloud tops. It is much fainter than either the A or B rings, often called the crepe ring or the dusky ring because of its dark gauzy appearance. The C ring is widely spaced. Its particles are smaller and farther apart than those in the brighter outer rings. Sunlight passes through the C ring fairly easily, giving it its translucent quality. Within the C ring are several narrow gaps, called the Maxwell gap, the Bond gap, and the Dawes gap. These narrow features were named after astronomers who contributed to the study of Saturn's rings. The Maxwell gap is named for James Clerk Maxwell, the Scottish physicist who, in 1859, first mathematically proved that Saturn's rings could not be solid but must be composed of many separate particles. The composition of the main rings is overwhelmingly water ice, about 95% or more by mass. The remaining few percent consists of smaller amounts of silicate dust, organic compounds, and other materials. The high purity of the ice is one of the reasons the rings appear so brilliantly white in good photographs. The particles in the main rings range enormously in size. The smallest are dust grains only a few micrometers across. Most of the visible material is in the size range of a few centimeters to a few meters. The largest blocks are estimated to be several tens of meters across, about the size of a house or small building. Even larger blocks may exist, but they are too rare to have been directly observed. Cassini measured the size distribution of ring particles by observing how the rings affected starlight passing through them. As Saturn moved past a background star, the changing brightness of the star as it shone through the rings provided detailed information about how many particles of each size were present in different parts of the ring system. The B ring is so thick in some places that even radio waves from spacecraft cannot easily pass through it. The Cassini spacecraft used radio occultation experiments, passing radio signals through the rings and measuring how they were attenuated to map the density of the rings in remarkable detail. The resulting maps showed structure on scales as small as a few hundred meters across. Even within the B ring, the density varies. There are subtle bright and dark bands, hundreds or thousands of them, each separated by tiny gaps. These features are sometimes called ringlets. They are created by complex gravitational and dynamical effects within the ring system, and many of them remain only partially understood. The A ring has its own characteristic structure. Near its outer edge are several density waves, spiral patterns created by the gravitational influence of moons orbiting just outside the ring. These waves spiral outward through the ring material, creating beautiful patterns visible in Cassini's images. Each wave is caused by a specific moon in a specific resonant orbital relationship. Inside the Encke gap of the A ring, the small moon Pan orbits Saturn. Pan is shaped roughly like a flying saucer, with a prominent equatorial ridge formed by accumulated ring material. As Pan orbits within the gap, its gravity sweeps the gap clear, keeping the surrounding ring material at a distance. The boundaries of the main rings are sharply defined in some places and gradual in others. The outer edge of the B ring is one of the most precise boundaries in the ring system, maintained by a gravitational resonance with the moon Mimas. The outer edge of the A ring is similarly sharp, kept in place by gravitational interactions with multiple nearby moons. Different colors are observed in Saturn's main rings depending on the wavelength of light used to view them. In visible light, the rings appear pale gold or white. In ultraviolet, certain regions appear bluer, indicating fresh, exposed ice. In infrared, the rings show subtle temperature variations that reveal information about the size and density of particles. The main rings also contain larger embedded objects that astronomers call propellers. These are small objects, perhaps half a kilometer across, that orbit within the rings and create distinctive propeller-shaped features in the surrounding material. Hundreds of propellers have been cataloged in Cassini imagery, each one a small body too tiny to be called a moon, but too large to be considered ordinary ring particle. Now gently, we will turn to one of the most striking features of Saturn's ring system, the wide dark gap called the Cassini division, along with the smaller Encke gap inside the A ring and the gravitational reasons these gaps exist. The Cassini division is the most prominent gap in Saturn's ring system. It is a wide, dark band visible even through small backyard telescopes, separating the brighter B ring on the inside from the slightly fainter A ring on the outside. The Cassini division is about 4,800 kilometers wide. That is roughly the distance from New York to Los Angeles. The Cassini division is named after the Italian-born astronomer Giovanni Domenico Cassini, who first discovered it in 1675. Cassini was working at the Paris Observatory using one of the best telescopes of his time. He noticed the dark gap between what we now call the A and B rings, becoming the first astronomer to recognize that Saturn's rings were not a single continuous structure. The Cassini division is not completely empty. Although it appears dark from a distance, it actually contains many smaller ring particles in relatively low concentrations. The density of material in the gap is roughly 1/20th of the density in the surrounding bright rings, through enough material to be detectable but too little to appear bright to the casual observer. Why does the Cassini division exist? The answer involves a gravitational phenomenon called orbital resonance. Particles at the inner edge of the Cassini division would orbit Saturn in exactly half the time it takes the moon Mimas to complete one orbit. This 2-to-1 resonance creates a regular gravitational push that gradually clears particles out of this specific orbital distance. Each time a ring particle in the resonant orbit approaches Mimas at the closest point in its loop, Mimas gives it a gentle gravitational nudge. Over many orbits, these repeated nudges add up. The particle's orbit is gradually stretched and changed until it is no longer in the resonant location. Over millions of years, this slow process has cleared the gap. The Cassini division itself contains its own internal structure. Within the larger gap are several narrower gaps, each named after a historical astronomer or scientist. The Huygens gap, the Laplace gap, and others sit within the broader Cassini division, creating a complex pattern of bands and gaps visible only in detailed Cassini imagery. Inside the A ring, there is another notable gap called the Encke gap. The Encke gap is much narrower than the Cassini division, only about 325 kilometers wide. It was discovered by the German astronomer Johann Encke in 1837. The gap is created and maintained by a small moon called Pan, which orbits directly within the gap itself. Pan is a tiny moon, only about 28 kilometers across. Despite its small size, its gravity is enough to sweep clear the surrounding ring material as it orbits within the Encke gap. Pan is roughly disc-shaped or oblate, with a prominent ridge of material around its equator. The ridge is made of ring particles that have accumulated on Pan over time. Beyond the Encke gap, near the outer edge of the A-ring, is an even smaller gap called the Keeler Gap. The Keeler Gap is only about 42 kilometers wide, and it is maintained by an even smaller moon called Daphnis. Daphnis is only about 8 kilometers across, but its gravity creates visible waves in the ring material on either side of its narrow gap. The waves created by Daphnis are some of the most beautiful features in Cassini's ring imagery. As Daphnis orbits, its gravity pulls nearby particles into wave-like patterns that ripple outward through the ring on both sides. The waves can be tens of kilometers tall, vastly larger than Daphnis itself. The contrast between the tiny moon and its enormous wave wake is striking. These shepherd moons within the ring system play an important role in maintaining the sharp edges of the gaps they inhabit. Without the moons, the gaps would gradually fill in with particles drifting from the surrounding ring material. The continuous gentle gravitational sweeping by the moons keeps the gaps cleared. Many other narrow gaps and bright ringlets appear throughout Saturn's ring system. Each one is the product of complex gravitational interactions between Saturn, its moons, and the ring particles themselves. The full catalog of these features is still being compiled by astronomers studying Cassini data many years after the mission ended. Some of the narrow ringlets within the Cassini division are eccentric, meaning they trace slightly elliptical paths rather than perfect circles. These eccentric ringlets are thought to be maintained by yet undiscovered small moons or by complex resonances with the moons that are known. Each one is a small mystery in its own right. From Earth, the Cassini division is one of the most reliable identifying features of Saturn through a telescope. Even a small backyard telescope can usually show the gap as a thin, dark line dividing the bright rings. Larger telescopes reveal more detail. The Encke gap is much harder to see from Earth, generally requiring a substantial telescope and excellent conditions. The naming of the gaps in Saturn's rings reflects the long history of telescopic observation of Saturn. From Cassini in the 17th century to Encke in the 19th to Keeler in the early 20th, each gap carries the name of a careful observer who contributed to humanity's understanding of this complex cosmic structure. The dark gaps in Saturn's rings, viewed against the brilliant brightness of the surrounding material, are a beautiful demonstration of how gentle gravitational forces acting persistently over millions of years can create sharp boundaries in a continuous medium. They are signatures of the slow cosmic patience that shapes the solar system. Now, gently, we will move outward from the main rings to the diffuse outer rings, the D, E, F, and G rings, each with their own characteristic structure and origin. Beyond the bright main rings of Saturn lie several fainter ring structures. The D ring is the innermost, lying closest to Saturn's cloud tops. The E, F, and G rings extend outward, some far beyond the orbits of inner moons. These outer rings are much less dense than the main rings, but they each have their own unique character and origin. The D ring is the innermost ring of Saturn. beginning at the inner edge of the sea ring and extending down toward Saturn's cloud tops. It is extremely faint and was not detected until the Voyager spacecraft visited Saturn in 1980 and 1981. The D-ring is composed mostly of fine dust particles, with very little of the larger ice material found in the bright rings. The dust particles in the D-ring are gradually falling into Saturn. They are caught by atmospheric drag and other forces, slowly spiraling downward over thousands of years. The constant rain of D-ring material into Saturn's upper atmosphere has been measured by Cassini and helps astronomers understand the ongoing erosion of the ring system as a whole. The F-ring is a narrow, bright structure just outside the A-ring. It was discovered by the Pioneer 11 spacecraft in 1979. The F-ring is remarkable for its complexity and dynamism. Unlike the broad main rings, the F-ring is a tight bundle of strands and clumps that twist and braid around each other. The ring is being constantly reshaped by the influence of two nearby shepherd moons. The two shepherd moons of the F-ring are called Prometheus and Pandora. They orbit Saturn just inside and just outside the F-ring, respectively. Their combined gravitational influence keeps the F-ring tightly confined to a narrow strip. Without these shepherd moons, the F-ring would have spread out and become much more diffuse over time. Prometheus is the inner shepherd of the F-ring. It orbits just inside the ring at a slightly faster rate than the ring particles. Each time Prometheus catches up to the F-ring, its gravity pulls some of the ring material slightly inward. The resulting disturbances create rippling features in the F-ring that change visibly over the course of just a few days. Pandora is the outer shepherd of the F-ring. It orbits just outside the ring at a slightly slower rate. The combined gravity of Pandora and Prometheus traps the F-ring in a confined orbit. The constant interactions between the moons and the ring create the bright clumps, dark gaps, and twisted strands that make the F-ring one of the most visually striking features in the Saturn system. The G-ring is much wider and more diffuse than the F-ring. It extends from about 165,000 to 175,000 kilometers from Saturn. The G-ring is faint enough that it was not detected until spacecraft visited Saturn. Most of its material is small dust grains with a small embedded clump of larger particles. The source of the G-ring material is a small moonlet called Aegeon, which orbits within the brightest part of the G-ring. Aegeon is tiny, only about half a kilometer across, but its gentle erosion by micrometeoroid impacts gradually releases small particles that spread outward to form the G-ring around it. The whole structure is essentially Aegeon's accumulated dust trail. The E-ring is the largest and most extended of all Saturn's rings. It begins at about 180,000 kilometers from Saturn and extends outward to nearly 500,000 kilometers, well beyond the orbits of several major moons. The E-ring is extraordinarily diffuse, made almost entirely of very fine ice particles. The source of the E-ring is Saturn's moon Enceladus. Geysers on Enceladus, which we will discuss in detail later, eject water and ice particles directly into space. Most of this material then becomes part of the E-ring as it spreads outward and around Saturn. Enceladus essentially feeds material into the E-ring on a continuous basis. The E-ring is brightest at the orbital distance of Enceladus, where its source material is being released. The ring fades both inward and outward from this central concentration. From inside the E-ring, the moon Enceladus orbits in a region of slightly thicker ring material, while the outer reaches of the ring are extremely faint and difficult to detect at all. Cassini flew through the E-ring many times during its mission. Each pass collected data on the size and composition of E-ring particles. The spacecraft confirmed that the particles are mostly water ice, with traces of salt and organic compounds, the same chemistry as the geysers of Enceladus. The link between Enceladus and the E-ring is among the strongest confirmed sources for any ring system in the solar system. Other faint ring structures also exist around Saturn. The Janus Epimetheus ring is a thin band of dust coincident with the orbits of two co-orbital moons. The Pallene ring is a faint band along the orbit of the small moon Pallene. Each of these tenuous structures represents material slowly accumulated from the gradual erosion of small moon. Saturn also has a vast invisible structure called the Phoebe ring. It is a very thin, very wide band of dust released from the small moon Phoebe, which orbits Saturn at a great distance and in the opposite direction from the inner moons. The Phoebe ring was discovered only in 1929 through observations by the Spitzer Space Telescope. It is virtually invisible in normal light, but glows faintly in infrared. The Phoebe ring is enormous. It extends from about 6 million to 13 million kilometers from Saturn, much farther than any other ring. The total volume of the Phoebe ring is greater than the volume of all Saturn's other rings combined, yet its density is so low that you could fly a spacecraft right through it without noticing anything. Now, gently, we will look closely at the individual particles that make up Saturn's rings, what they are made of, how big they are, and how they behave as they orbit Saturn in their patient cosmic dance. Saturn's rings, despite their appearance of solid bands from a distance, are composed of countless individual particles. Each particle orbits Saturn independently, following its own gentle path around the planet. The interactions between these particles, combined with the gravitational influence of nearby moons, create the complex structure of the ring system. The vast majority of ring particles are made of water ice. About 95% or more of the ring material by mass is water ice, with the remaining few percent consisting of small amounts of silicate dust, organic compounds, and other materials. The high purity of the ice is one of the reasons the rings appear so bright and white in good photographs. The particles range enormously in size. The smallest are tiny dust grains, only a few micrometers across, smaller than a human hair. The most common ring particles are in the size range of a few centimeters to a few meters, similar to small stones or boulders. The largest particles are estimated to be several tens of meters across, comparable to a house or small building. The shapes of ring particles are highly varied. Some are roughly spherical, having been smoothed by gentle collisions over long periods of cosmic time. Others are irregular, having recently been broken from larger pieces. The largest blocks may be elongated or oddly shaped. In all cases, the particles tumble slowly as they orbit, gradually wearing each other smooth. Ring particles collide with each other regularly. Most of these collisions are gentle, occurring at low relative velocities. The particles bounce off each other or stick together briefly before separating again. Occasionally, more energetic collisions break particles into smaller pieces, while other collisions cause smaller particles to accumulate into larger ones. The temperature of ring particles varies depending on their location and exposure to sunlight. On the sunlit side, particles can reach temperatures of about -170 degrees Celsius. On the shadowed side, the temperature drops to nearly -200 degrees. Throughout the rings, the temperature is far below the freezing point of water, ensuring that the ice particles remain solid. Despite being almost pure water ice, Saturn's rings vary slightly in color across different regions. Some parts appear distinctly more red, others more blue. These color differences likely reflect small amounts of contamination by darker materials, perhaps organic compounds or fine silicate dust. The reddish patches are sometimes called the dirty regions of the rings. Cassini measurements have allowed astronomers to estimate the total mass of all the ring material. The current best estimate is about 1/40th the mass of Saturn's moon Mimas, significantly less than once thought. This small mass is one reason astronomers now believe the rings may be relatively young, having formed perhaps only 100 million years ago. The ring particles are slowly being lost to Saturn. Several processes contribute to this loss. Micrometeoroid impacts kick particles into atmospheric drag at the inner edge. Ice sublimation at higher temperatures gradually erodes the particles. Solar wind and Saturn's magnetic field can ionize and remove some material. Together, these processes mean the rings are gradually thinning over time. If the rings are indeed only 100 million years old, they formed long after Saturn itself was already mature. The leading theory is that a comet or icy moon strayed too close to Saturn at some point in the past, was torn apart by Saturn's gravity, and its remnants spread into the ring system we see today. This event would have been spectacular, but is now hidden in the deep cosmic past. Ring particles within the same orbit gradually arrange themselves into thin layers due to their mutual gravitational attraction. These self-organized patterns are called wakes. Each wake is a long, thin clump of ice, oriented in a specific direction relative to the orbital motion. The pattern of wakes contributes to the overall optical properties of the rings. Cassini directly photographed some of the largest individual ring particles. These photographs revealed strange and surprising shapes, irregular blocks of ice with prominent ridges, accumulated dust on their surfaces, and complex orbital companions. Each large particle is a small world in its own right, with its own slow history of collisions and accumulation. The smallest particles, those just a few micrometers across, behave very differently from the larger blocks. They are strongly influenced by sunlight pressure and Saturn's magnetic field. They can be pushed outward or drawn inward by these subtle forces, sometimes leaving the main ring entirely. The behavior of these tiny dust particles is responsible for many of the faint outer ring features. Some ring particles eventually fall into Saturn's atmosphere. As they enter the upper atmosphere, they vaporize and contribute small amounts of water and chemicals to Saturn's clouds. This material rain has been measured by spacecraft instruments, providing a direct connection between the rings and the planet's atmosphere. Among the most interesting findings from Cassini was the discovery that Saturn's rings rain into the upper atmosphere far more than expected. The rate of ring material loss is high enough that, at present rates, the rings may persist for only a few 100 million more years before disappearing entirely. This makes the rings, in cosmic terms, a temporary feature. Tonight, the rings of Saturn continue their slow, ancient dance. Countless particles, large and small, drift in their patient orbits. Some collide gently, some merge, some break apart. The whole vast structure rotates around Saturn at speeds varying with orbital distance, fastest near the planet, slowest at the outer edges. The rings have been turning quietly for at least 100 million years. Now, gently, we will move from the rings themselves to the moons of Saturn, beginning with the largest of all, Titan, the only moon in the solar system to have a substantial atmosphere and one of the most surprising worlds in the entire solar system. Titan is the largest moon of Saturn and the second largest moon in the entire solar system. Only Jupiter's moon Ganymede exceeds it in size. Titan is so large that if it orbited the Sun directly, it would be considered a planet. It is even larger than the planet Mercury, although less massive due to its lower density. Titan was discovered in 1655 by the Dutch astronomer Cassini-Huygens, the same astronomer who later correctly identified Saturn's rings. Huygens was looking through one of the best telescopes of his time, and Titan appeared as a small, distinct point of light near Saturn. He named the discovery simply Luna Saturni, meaning the moon of Saturn. The most remarkable feature of Titan is its atmosphere. Titan is the only moon in our solar system to have a substantial atmosphere, and that atmosphere is denser than Earth's. The surface pressure on Titan is about 1.5 times the pressure at sea level on Earth. The atmosphere is composed primarily of nitrogen with about 5% methane and small amounts of other compounds. Sunlight on Titan is filtered through the thick haze of its atmosphere. The result is a dim orange or yellow glow at the surface, similar in brightness to a heavily overcast day on Earth at twilight. Direct sunlight never reaches the surface. The haze layer completely blocks the disk of the sun, although enough light filters through to illuminate the landscape softly. The temperature on Titan's surface is extremely cold, about -179 degrees Celsius. At this temperature, water ice is as hard as rock. The bedrock of Titan is largely made of water ice. Many features that on Earth would be rock are, on Titan, frozen water ice exposed to the surface conditions of an alien world. Titan has lakes, rivers, and seas, but these bodies of liquid are not water. Water would be frozen solid at Titan's surface temperature. Instead, Titan's lakes are made of liquid methane and ethane. These hydrocarbons remain liquid at Titan's temperature, similar to how water remains liquid on Earth. The largest lake, Kraken Mare, covers an area larger than the Caspian Sea. Titan has weather. There are clouds of methane droplets, methane rain, and methane snow. The methane forms rivers that flow downhill across the icy landscape, carving channels much like rivers of water do on Earth. After heavy rains, parts of Titan briefly experience flash flooding before the methane drains back into the lakes and seas. Wind patterns on Titan are slow but persistent. The thick atmosphere means that even modest wind speeds carry significant force. The winds create vast fields of dunes across Titan's equator. These dunes are made not of sand but of organic particles, complex hydrocarbons that have settled out of the atmosphere over billions of years. The dunes stretch for hundreds of kilometers. In 2005, the European Space Agency probe Huygens descended through Titan's atmosphere and landed safely on the surface. This remains the only spacecraft landing on any moon beyond Earth's moon. Huygens transmitted data for about 90 minutes from the surface before its batteries failed, returning the only photographs ever taken of Titan's surface. The Huygens probe revealed a remarkable scene. Smooth orange-brown plains stretched in every direction. Rounded pebbles of water, ice covered the ground, evidence of past flowing methane. Channels carved by methane rivers were visible nearby. The temperature at the landing site was a steady minus 180 degrees Celsius. Below Titan's icy surface lies a layer of liquid water, a subsurface ocean. This ocean is kept liquid by a combination of tidal heating from Saturn's gravity and the natural heat retained from Titan's formation. The ocean may be hundreds of kilometers deep, sitting between the icy crust above and a deeper layer of high-pressure ice below. The chemistry of Titan is extraordinarily complex. In its atmosphere, sunlight breaks apart nitrogen and methane molecules, which then recombine into a vast variety of complex organic compounds. These compounds drift down to the surface, where they accumulate as the dark dunes and the organic mud that coats the landscape. Titan's atmospheric chemistry produces some of the building blocks of life as we know it. Could there be life on Titan? It is one of the great open questions in astrobiology. The combination of liquid water in the subsurface ocean, complex organic chemistry in the atmosphere and on the surface, and a long, stable history make Titan one of the most interesting places to search for life beyond Earth. Future missions are being planned to investigate this possibility more thoroughly. Titan orbits Saturn at a distance of about 1,200,000 kilometers. Each orbit takes about 16 days. Titan is tidally locked to Saturn, meaning the same face always points toward the planet. From the surface of Titan, on the side facing Saturn, you would always see Saturn looming overhead, although the thick haze would prevent any sharp view of the planet's details. A future NASA mission called Dragonfly is planned to land a rotorcraft on Titan in 2034. Dragonfly will be able to fly between different landing sites, exploring multiple regions of Titan's varied landscape. It will be the first aircraft ever to fly on another world, and it will return enormous amounts of new information about this complex moon. Tonight, on the cold, misty surface of Titan, methane rain may be falling somewhere. Methane rivers may be flowing slowly toward methane seas. The thick haze drifts overhead, blocking the dim orange sunlight. Saturn looms enormous in the sky above one hemisphere. The dunes lie quiet, the seas lie quiet, the whole vast landscape extending in patient cosmic stillness. Now gently, we will move from the great hazy Titan to a very different kind of moon, the small icy Enceladus, with its geysers and hidden ocean and surprising signs of warmth deep inside. Enceladus is one of the most surprising moons in the entire solar system. It is small, only about 500 kilometers across, about 1/7 the diameter of our moon. From a distance it appears as a smooth, icy white world. But the surface of Enceladus is fractured, and from those fractures plumes of water ice erupt continuously into space. Enceladus was discovered in 1789 by the British astronomer William Herschel. For nearly 2 centuries afterward, it appeared to be just another small icy moon of Saturn. Voyager spacecraft images in the 1980s showed that Enceladus had an unusually smooth and bright surface, suggesting active resurfacing, but the cause was not yet understood. The full picture of Enceladus emerged in 2005 when the Cassini spacecraft made close passes by the moon. During one approach, Cassini detected a plume of water vapor and ice particles being ejected into space from the South Polar region. This discovery transformed Enceladus from a quiet curiosity into one of the most active and interesting bodies in the solar system. The plumes erupt from a series of long parallel cracks at Enceladus's south pole, Called the tiger stripes because of their distinctive appearance, the four main tiger stripes are each about 130 kilometers long. They cross the South Polar region in a pattern of nearly parallel lines. From these cracks, water and ice continuously stream outward into space. The plumes are powered by water from a subsurface ocean. Below the icy crust of Enceladus, all the way around the Moon, lies a global ocean of liquid water. This ocean is kept liquid by tidal heating, the gentle flexing of Enceladus caused by its orbital relationship with Saturn and other moons. The ocean is several kilometers deep and surrounds a small rocky core. The ocean water reaches the surface through cracks in the ice. As the water emerges into the near vacuum of space, most of it instantly freezes into tiny ice particles. Some boils off as water vapor. The resulting plumes rise hundreds of kilometers above the surface before either escaping into space or falling back to Enceladus as snow. Cassini flew directly through the Enceladus plumes multiple times during its mission. By analyzing the materials in the plumes, scientists could indirectly sample the subsurface ocean. The plume material contained water, salts, ammonia, simple organic molecules, and other compounds. Most surprisingly, it contained molecular hydrogen, a strong sign of hydrothermal activity in the deep ocean. The presence of molecular hydrogen in the plumes suggests that hot water is interacting with rock at the bottom of Enceladus's ocean. On Earth, similar hydrothermal vents at the bottom of oceans support entire ecosystems of life, drawing energy from chemical reactions rather than sunlight. The conditions at the bottom of Enceladus's ocean may be similar. This makes Enceladus one of the most promising places to search for life beyond Earth. The combination of liquid water, energy sources, and complex chemistry, all the conditions that are believed necessary for life, exists right now beneath Enceladus's icy surface. Whether life actually exists, there remains unknown, but the conditions are ideal. Despite its small size, Enceladus is one of the few worlds in the solar system that is currently geologically active. Most small moons cool quickly after their formation and become inert, but Enceladus continues to release heat from its interior, kept warm by tidal flexing and possibly other processes still being investigated. The total power output from Enceladus's interior is estimated to be about 16 gigawatts. This is a modest amount in cosmic terms, comparable to the output of a few large nuclear power plants, but it is more than enough to maintain the subsurface ocean and drive the continuous plume activity. The source of this heat is still being studied in detail. Cassini observed the plume activity for years. The plumes varied over time, with some periods of more vigorous activity and other periods of relative calm. The variations seem to correlate with Enceladus's position in its orbit around Saturn, suggesting that tidal stresses opening and closing the tiger stripe cracks control the timing of eruptions. The ice that escapes Enceladus's gravity becomes part of the E-ring around Saturn. The continuous outpouring of material from Enceladus is the primary source of the E-ring's icy particles. Enceladus is essentially feeding Saturn's vast outer ring with its own subsurface ocean water in a slow, ongoing cosmic exchange. Around the rest of Enceladus's surface, away from the South Pole, the Moon is covered in different types of icy terrain. There are ancient cratered regions, smoother resurfaced areas, and complex fracture patterns that suggest a long history of geological activity. The northern hemisphere is heavily cratered, indicating that it has been relatively quiet for a long time. Future missions to Enceladus are being planned by multiple space agencies. The proposed Enceladus Orbolander would orbit Enceladus and then land on its surface, sampling material that has fallen back from the plumes. Such a mission could directly search for signs of life in the chemistry of the moon. The science would be unprecedented. Tonight, on Enceladus, the plumes continue to erupt. Water from the hidden ocean far below rises through the tiger stripe cracks and bursts into the cosmic vacuum. Most of it freezes instantly into a glowing white spray of ice particles. Some of those particles will eventually settle back onto Enceladus as snow. Others will join the E-ring around Saturn. Now, gently, we will turn from the active Enceladus to several of Saturn's other moons, the quiet, icy worlds of Mimas, Tethys, Dione, and Rhea, each with their own characteristics and history. Among Saturn's many moons are 4 mid-sized icy worlds that fill the space between tiny Enceladus and the giant Titan. They are called Mimas, Tethys, Dione, and Rhea. Each is a few hundred kilometers across. Each is composed primarily of water ice, and each tells its own quiet story of the early solar system. Mimas is the innermost of these 4 moons. It is about 396 kilometers across, small enough that its gravity barely pulls it into a spherical shape. Mimas is most famous for the enormous crater that dominates its surface, called Herschel. The crater is 130 kilometers across, making it nearly a third the diameter of Mimas itself. The enormous size of the Herschel crater compared to Mimas itself gives the moon a distinctive appearance. From certain angles, Mimas looks remarkably like the Death Star from the Star Wars films, a comparison that astronomers often make when introducing the moon. The crater was formed by an impact billions of years ago that nearly shattered Mimas entirely. Mimas was discovered in 1789 by William Herschel, the same astronomer who discovered Uranus. The Herschel crater is named in his honor. Mimas was named after one of the giants in Greek mythology, a tradition for Saturn's moons that continues to this day, with most major moons receiving names from classical mythology. Recent research has suggested that Mimas may actually have a subsurface ocean of liquid water, similar to those on Enceladus and Europa. The evidence comes from subtle variations in Mimas's rotation that suggest its rocky core is loose within an icy shell, with a liquid layer in between. If confirmed, Mimas would join the small but growing list of ocean worlds in the solar system. Tethys is the next moon out from Mimas. It is much larger, about 1,060 kilometers across, more than twice the size of Mimas. Tethys was discovered in 1684 by Giovanni Cassini, the same astronomer who discovered the gap in Saturn's rings. Tethys is one of the brightest icy moons in the solar system, reflecting most of the sunlight that strikes its surface. Tethys has its own enormous crater called Odysseus on one side of the moon. Like Mimas's Herschel, the Odysseus crater is huge in proportion to the moon itself, about 450 kilometers across, or roughly 40% of Tethys's diameter. The impact that formed Odysseus nearly destroyed Tethys. Tethys also has an extraordinary geological feature called Ithaca Chasma, a vast canyon that runs for over 2,000 kilometers across the moon's surface. The chasm is up to 100 kilometers wide and several kilometers deep. It is one of the longest geological features in the solar system, stretching from near the North Pole to near the South Pole. Dione is the next major moon outward from Tethys. It is about 1,120 kilometers across, slightly larger than Tethys. Dione was discovered in 1684, also by Cassini. The surface of Dione is heavily cratered, but also shows extensive networks of bright streaks crossing parts of its terrain. These bright streaks are tectonic fractures, where the icy surface has split and exposed fresh ice. Dione has its own faint ring system, at least. There are signs of one. Material extends along Dione's orbit, possibly trapped by gravitational interactions with the Moon. The Dione ring is far too faint to be seen from Earth, but Cassini detected hints of its existence. The full extent and behavior of this ring remain subjects of ongoing study. Dione also has two small companion moons that orbit Saturn at the same distance as Dione itself. Helene orbits ahead of Dione at the L4 Lagrange point, and Polydeuces orbits behind Dione at the L5 Lagrange point. These tiny companions are stable in their positions due to the specific gravitational geometry of the Saturn-Dione system. Rhea is the second largest moon of Saturn after Titan. It is about 1,528 kilometers across, significantly larger than Mimas, Tethys, and Dione. Rhea was discovered in 1672 by Giovanni Cassini. The surface of Rhea is heavily cratered, with some craters showing the structure of complex impact features. Rhea has very thin oxygen and carbon dioxide atmosphere. The atmosphere is extremely tenuous, about 5 trillion times less dense than Earth's atmosphere, but detectable. The source of this atmosphere is thought to be the breakdown of water ice on Rhea's surface by impacts from charged particles in Saturn's magnetic field. Rhea has been observed to possibly have a faint ring system as well, similar to Dione. Hints of ring material extending along Rhea's orbit were detected by Cassini, although the existence and nature of these rings are still debated by astronomers. If confirmed, Rhea would be the second moon known to have its own ring system in addition to its parent planet. All four of these mid-sized moons, Mimas, Tethys, Dione, and Rhea, orbit relatively close to Saturn and within the outer reaches of the bright ring system. They are tidally locked to Saturn, meaning the same face always points toward the planet. From their surfaces, Saturn appears very large in the sky, with its rings appearing as a thin line at certain viewing angles. These quiet, icy moons have orbited Saturn for billions of years. Their surfaces preserve the cratering record of the long history of the solar system. The largest craters tell of catastrophic ancient impacts. The smaller craters tell of the slow, steady reign of smaller bodies. Each moon is a quiet historical archive of the early outer solar system. Now, gently, we will turn to one of the most strange and surprising moons of Saturn, Iapetus, the two-faced moon, with one side as bright as snow and the other as dark as coal. Iapetus is one of the most puzzling moons in the solar system. It is large, about 1,500 kilometers across, similar in size to Rhea, and it orbits Saturn at a great distance, far beyond most other moons. But what makes Iapetus truly remarkable is its surface. One hemisphere is as bright as fresh snow, the other is as dark as charcoal. Iapetus was discovered in 1671 by Giovanni Cassini. Cassini noticed something strange about the moon almost immediately. He could see it easily when it was on one side of Saturn, but it disappeared from view when it was on the other side. He correctly deduced that one hemisphere must be much darker than the other, and that Iapetus must be tidally locked to Saturn. The bright hemisphere of Iapetus, called Cassini-Reggio's neighbor, or the trailing hemisphere, is composed of relatively pure water ice. It reflects most of the sunlight that strikes it and appears bright white from a distance. The dark hemisphere, called Cassini-Reggio, is covered with a thin layer of dark material that absorbs most of the sunlight. The dark material on Cassini-Reggio is rich in carbon and organic compounds. Where does this material come from? The leading theory is that it has been swept up by Iapetus over millions of years as the Moon orbits through a region of space populated by debris from one of Saturn's outer moons. Specifically, the dark material is believed to come from Phoebe. Phoebe is a small outer moon of Saturn that orbits in the opposite direction from the inner moons. Phoebe is dark and rich in organic compounds. Tiny dust particles slowly chipped from Phoebe's surface by micrometeoroid impacts drift inward toward Saturn over millions of years. When Iapetus passes through this dust cloud, the dust accumulates on the leading hemisphere, the side facing forward in its orbital motion. Once enough dark material has accumulated, the leading hemisphere of Iapetus begins to warm slightly more than the trailing hemisphere because dark surfaces absorb more sunlight. This warming causes ice to sublimate, to turn from solid directly to vapor, leaving behind even more dark material. Meanwhile, the sublimated ice migrates to the colder trailing hemisphere, where it freezes out as fresh white ice. This process creates a positive feedback loop. The dark side gets darker as more ice escapes. The bright side gets brighter as more ice accumulates. Over billions of years, the contrast between the two hemispheres has become more and more extreme. This is why Iapetus has the most pronounced hemispheric asymmetry of any moon in the solar system. In addition to its two-faced nature, Iapetus has another extraordinary feature, a massive equatorial ridge that runs almost halfway around the Moon. The ridge is up to 20 kilometers high and 20 kilometers wide, with extremely steep slopes. It precisely follows Iapetus's equator. Few features anywhere in the solar system are as geometrically distinctive. The origin of Iapetus's equatorial ridge is still not fully understood. Several theories have been proposed. One suggestion is that the ridge represents material that fell to Iapetus from a now vanished ring around the Moon. Another is that it was created by tectonic activity during a period when Iapetus rotated much faster than it does today. Iapetus rotates very slowly. A single Iapetus day lasts about 79 Earth days, the same as the time it takes to complete one orbit around Saturn. Iapetus is the only large moon of Saturn that is not particularly close to its planet. It orbits about 3.5 million kilometers from Saturn, more than 3 times the distance of Titan. From the surface of Iapetus, Saturn would appear noticeably smaller than from the inner moons, but it would still be a striking sight. The ring system would be visible at a steep angle since Iapetus's orbit is tilted significantly from Saturn's equatorial plane. The rings would appear thinner and more inclined than from closer moons. The Cassini spacecraft made several close passes by Iapetus during its mission. The detailed imagery revealed the sharp boundary between the dark and bright hemispheres, the extraordinary equatorial ridge, and many smaller features. Cassini's observations gave scientists the most complete picture of this strange moon that has ever been obtained. Iapetus has a low density, indicating that it is composed primarily of water ice with a relatively small rocky core. Its interior structure is simpler than that of larger moons like Titan, but it still preserves a record of conditions in the early solar system when it formed. The Moon has been geologically quiet for most of its history. There are no plans currently for a dedicated mission to Iapetus. The Moon's great distance from Saturn makes it difficult to reach. Most Saturn system missions focus on the inner moons and rings, but the secrets of Iapetus's two-faced surface and its equatorial ridge continue to intrigue scientists, and a future mission to better understand this moon remains a possibility. Tonight on Iapetus, the dark hemisphere faces forward through space, slowly sweeping up more dust from the cosmic environment. The bright hemisphere faces backward, accumulating fresh ice from sublimation processes. The equatorial ridge runs unbroken around the equator. The Moon rotates slowly in its long elliptical orbit around Saturn. Iapetus stands as one of the most distinctive examples of how cosmic processes acting over very long times can create extraordinary visible patterns. The Moon's striking appearance, the result of billions of years of slow accumulation and migration, demonstrates the patient power of small effects when given enough cosmic time. Now, gently, we will turn from the two-faced Iapetus to one of the strangest small moons of Saturn, Hyperion, which has a porous, sponge-like appearance unlike anything else in the solar system. Hyperion is one of the strangest moons in the entire solar system. It is small, only about 300 kilometers across at its longest dimension, but its appearance is unlike any other body that has ever been observed. The surface of Hyperion is covered with thousands of deep, round pits, giving it the appearance of an enormous sponge or a piece of porous coral. Hyperion was discovered in 1848, almost simultaneously by two different astronomers, William Lassell in England and William and George Bond in the United States. The discovery was made just days after the rings of Neptune were photographed for the first time. Hyperion was the first moon ever discovered that was not roughly spherical. Hyperion is the largest irregularly shaped moon in the solar system. Most moons of similar size or larger are pulled into roughly spherical shapes by their own gravity. Hyperion, despite being a substantial body, is not. Its overall shape is elongated and roughly potato-like, suggesting that it may be a fragment of a larger ancient body that was broken apart by a collision. The Cassini spacecraft made close passes by Hyperion and captured remarkably detailed images. These photographs revealed the moon's bizarre surface in great detail. Every crater on Hyperion is unusually deep, much deeper than craters of comparable size on other moons. The deep craters give Hyperion its distinctive sponge-like appearance. Why are the craters on Hyperion so deep? The answer lies in Hyperion's low density and high porosity. Hyperion is one of the least dense major moons known, with a density only about half that of water. This indicates that the moon is composed of very loosely packed material, perhaps with large empty spaces between solid components. The interior may be more like a sponge than a solid rock. When meteoroids strike Hyperion, the impact compacts the surrounding material rather than ejecting it the way impacts do on denser bodies. This produces unusually deep crater pits surrounded by dark material that has been pressed downward. The cumulative effect of countless impacts over billions of years has created the distinctive spongiform appearance. The composition of Hyperion is primarily water ice with some rocky material mixed in. The bottoms of the deep pits often appear darker than the rims, suggesting that organic compounds and other dark materials have accumulated in the shadowed regions. The contrast between the bright, icy rims and the darker pit floors gives Hyperion its mottled, patchy appearance. Hyperion has one of the most unusual rotational behaviors in the solar system. It rotates chaotically. Unlike almost all other moons, Hyperion is not tidally locked to Saturn. Its rotation axis tumbles unpredictably, with the moon's orientation in space changing in complex ways over each orbit. There is no fixed rotational pole on Hyperion. The chaotic rotation results from a combination of factors: Hyperion's elongated shape, its eccentric orbit around Saturn, and the gravitational influence of nearby Titan all combine to make stable tidal locking impossible. The result is that any prediction of which direction Hyperion will face at a future time becomes essentially impossible beyond a few weeks. Despite Cassini's close passes by Hyperion, predictions of which side the spacecraft would see during each encounter were essentially educated guesses. The mission team had to be prepared for any possible orientation. Each new image revealed a different aspect of the moon, never quite repeating itself. Hyperion orbits Saturn at a distance of about 1.5 million kilometers, slightly farther out than Titan. Hyperion is locked in a resonance with Titan, completing exactly 3 orbits for every 4 orbits of Titan. This 4-to-3 resonance is part of what creates Hyperion's irregular rotation. If you could stand on the surface of Hyperion, the experience would be unusual. The gravity would be very low, only about 2% of Earth's gravity. A person could easily jump several meters into the air. The horizon would be very close due to Hyperion's small size and irregular shape, and the sky would contain Saturn looming nearby, with stars wheeling chaotically as Hyperion tumbled through space. Hyperion's strange characteristics raise interesting questions about its origin. Some scientists have proposed that Hyperion is a captured object from the outer solar system, perhaps a body that originally formed in the Kuiper belt and was later captured into orbit around Saturn. Its unusual porosity and composition would be consistent with such an origin. Other scientists believe Hyperion may be a remnant of a larger ancient moon that was shattered in a catastrophic collision long ago. In this scenario, Hyperion would be one of the largest surviving fragments. The other pieces from the collision may have reaccumulated into smaller bodies or been ejected from the Saturn system entirely. Hyperion is the largest known body with such an extreme porous surface. Smaller similar bodies likely exist throughout the solar system, but they are too small to be easily detected. As humanity continues to explore the outer solar system, more bodies similar to Hyperion may be discovered. Each one would add to our understanding of the diversity of small worlds. Tonight, Hyperion continues to tumble silently through space. Its sponge-like surface, the result of countless ancient impacts on its porous structure, faces in some direction that no one can predict. The deep pits accumulate cosmic dust. The bright rims reflect what little sunlight reaches this distant region of the solar system. Now, gently, we will move from the strange Hyperion to the small shepherd moons that maintain Saturn's ring system. Tiny bodies like Pan, Atlas, Prometheus, and Pandora, each playing a crucial role in keeping the ring structure organized. Saturn has a remarkable collection of tiny moons that orbit within or near the ring system. These small moons, called shepherd moons or ring moons, play a crucial role in maintaining the structure of Saturn's rings. They sweep clear the gaps between rings, define the sharp edges of ring boundaries, and create wave patterns in the surrounding material. Pan is one of the most distinctive of these small moons. It is shaped roughly like a flying saucer or a flat dumpling, with a prominent ridge running around its equator. Pan is about 28 kilometers across at its widest. It orbits within the Encke gap of Saturn's ring, sweeping the gap clear as it moves. The unusual shape of Pan was a surprise when Cassini first photographed it in detail. The equatorial ridge is made of accumulated ring particles that have stuck to Pan over millions of years. Pan's orbital path keeps it precisely at the radius where ring particles would naturally accumulate at the equator of any small body in that location. Atlas is another small moon with a similar shape to Pan. Atlas orbits just outside the A-ring, helping to define the outer edge of the A-ring. Like Pan, Atlas has a prominent equatorial ridge. Atlas is slightly larger than Pan, about 30 kilometers across at its widest. The two moons are sometimes called twins, despite their different orbital positions. Daphnis is even smaller than Pan or Atlas. It is only about 8 kilometers across, the size of a small mountain. Daphnis orbits within the Keeler Gap, a very narrow gap in Saturn's A-ring near its outer edge. Despite its tiny size, Daphnis creates spectacular wave patterns in the ring material on either side of the gap. The waves created by Daphnis are some of the most beautiful features Cassini ever photographed. As Daphnis orbits, its gravity pulls particles from the inner edge of the adjacent ring slightly outward, then releases them. The same happens with particles on the outer edge of the other adjacent ring, pulled slightly inward. The result is a series of waves that propagate through the ring material. Prometheus is one of the most active shepherd moons. It orbits just inside the F-ring of Saturn, where its gravity constantly disturbs the F-ring particles. Prometheus is about 136 kilometers long, but elongated and irregularly shaped. As it moves along its orbit, Prometheus passes very close to the F-ring at certain points, pulling streams of ring material toward itself. Each close approach of Prometheus to the F-ring creates distinctive dark grooves in the ring. These grooves are visible in Cassini imagery and have been carefully tracked over years. The patterns evolve slowly as Prometheus and the F-ring particles complete their orbits at slightly different rates. The dynamic interaction is one of the most observed examples of ring-moon interaction. Pandora orbits just outside the F-ring. Together with Prometheus on the inside, Pandora helps to confine the F-ring to a narrow strip. Pandora is about 81 kilometers long. The gravitational influence of both moons keeps the F-ring particles in a tight orbital corridor, preventing them from spreading out into a wider ring. Janus and Epimetheus are two larger small moons that orbit Saturn in a remarkable shared orbit. They are co-orbital, meaning they orbit Saturn at almost exactly the same distance. However, because they are at slightly different orbital radii, they would eventually catch up to each other. The remarkable behavior is that when they approach, they exchange orbits. Each moon takes over the other's orbital path. Janus is about 178 kilometers across, while Epimetheus is about 116 kilometers across. The orbital exchange happens about every 4 years. From the perspective of one moon, the other appears to approach, slow down, reverse direction, and recede, all while remaining at approximately the same distance from Saturn. Other small moons of Saturn include a Geion, which orbits within the G-ring, Methone, an unusual smooth and egg-shaped moon, Anthe, a tiny moon in a narrow arc of material, and Pallene, named after one of the giants of Greek mythology. Each of these small bodies, just a few kilometers across, contributes to the complex dynamics of Saturn's ring system. The discoveries of many of these small moons came from careful analysis of Cassini imagery. Some of them were too faint to be reliably detected before Cassini arrived. The total moon count of Saturn has grown substantially since Cassini's mission ended, as researchers continue to find new tiny bodies in archival images. Saturn currently has more than 140 known moons, more than any other planet in the solar system. Most of these moons are very small, just a few kilometers across. The total count keeps growing as new searches reveal more small bodies in distant orbits or hidden within the ring system. The Saturn system is among the most populous in the solar system. The discovery of these shepherd moons has revolutionized understanding of how Saturn's rings maintain their sharp structure. Before the spacecraft era, astronomers were puzzled by why the rings did not simply spread out and become more diffuse over time. The shepherd moons, with their precise gravitational influence on the ring material, provide the answer. Tonight, the shepherd moons of Saturn continue their patient work. Pan sweeps the Encke gap clear. Daphnis creates its beautiful waves. Prometheus and Pandora confine the F-ring. Janus and Epimetheus prepare for their next orbital exchange. The whole ring system, with all its complex structure, depends on these small gravitational guardians. Now, gently, we will turn from the shepherd moons of the rings to a broader feature of Saturn, its enormous magnetic field, which envelops the planet and its many moons and creates beautiful auroras above the polar regions. Saturn has one of the most powerful magnetic fields of any planet in the solar system. The magnetic field is generated deep within Saturn, in the layer of metallic liquid hydrogen that surrounds the planet's small, dense core. As Saturn rotates rapidly, this conducting fluid generates electric currents that produce the planet's magnetic field through a process called the dynamo effect. Saturn's magnetic field is somewhat weaker than Jupiter's, but much stronger than Earth's. The field strength at Saturn's cloud tops is about 500 times stronger than the magnetic field at Earth's surface. The field extends far out into space, reaching about 1,000,000 kilometers from the planet, more than a third of the way to the moon Titan. One of the most unusual features of Saturn's magnetic field is its near-perfect alignment with the planet's rotational axis. Most other planets have magnetic fields tilted at significant angles from their rotation axes. Earth's magnetic field, for example, is tilted by about 11 degrees from the rotational axis, but Saturn's magnetic field is tilted by less than 1 degree. This near-perfect alignment is a great puzzle for theorists. The magnetic field of Saturn creates a vast region of space around the planet called the magnetosphere. Within the magnetosphere, charged particles from the Sun and from Saturn's moons are trapped by the magnetic field. These charged particles spiral along magnetic field lines, sometimes for years before either escaping or being absorbed into Saturn's atmosphere or its moons. The solar wind, a continuous stream of charged particles flowing outward from the Sun, pushes against Saturn's magnetosphere on the Sun-facing side. This creates a bow shock similar to the wave formed in front of a ship moving through water. On the side facing away from the Sun, the magnetosphere stretches out into a long tail extending millions of kilometers behind Saturn. Where the magnetic field lines come down to Saturn's poles, charged particles can spiral into the upper atmosphere. When these high-energy particles collide with atoms and molecules in Saturn's atmosphere, they excite those particles to higher energy levels. As the atoms and molecules relax back to their normal state, they emit light. This is the cause of Saturn's auroras. Saturn's auroras are most easily seen in ultraviolet light. From spacecraft equipped with the right cameras, the auroras appear as bright rings of light around each magnetic pole. The northern and southern auroral rings change shape and brightness in response to variations in the solar wind. During solar storms, the auroras can become extremely bright and dynamic. In visible light, Saturn's auroras appear soft pink, purple, or blue. The exact color depends on which atmospheric molecules are being excited and at what altitude. Methane and hydrogen produce different colors than the nitrogen and oxygen that create Earth's auroras. The aurora colors are subtle and require sensitive instruments to capture properly. Cassini observed Saturn's auroras in great detail for many years. The patterns of the auroras change continuously as the solar wind varies and as Saturn rotates. Long exposure images and time-lapse sequences captured the slow choreography of the auroras over time. Each new view revealed something different about how the magnetosphere interacted with the solar environment. Some moons of Saturn play a role in the magnetosphere. The icy plumes of Enceladus, for example, feed water and other ions into Saturn's magnetosphere. These ions become part of the trapped particle population, eventually contributing to the auroral light shows. There is a direct connection between activity on Enceladus and the auroras at Saturn's poles. Titan, the largest moon, has its own interaction with the magnetosphere. As Titan orbits within Saturn's magnetic field, the field strips away particles from Titan's upper atmosphere. This slow loss of atmospheric material to space affects Titan's long-term atmospheric evolution. Over billions of years, this slow erosion has changed the composition of Titan's atmosphere. Saturn's magnetic field rotates with the planet. This means that as Saturn rotates roughly every 10.5 hours, the entire magnetosphere rotates as well. The rotation of the magnetic field carries trapped, charged particles along with it. Saturn's rapid rotation is one reason its magnetosphere is so dynamic and energetic. In addition to the auroras, Saturn's magnetic field is responsible for radio emissions detectable across millions of kilometers. These radio waves are generated by charged particles spiraling in the magnetic field near the poles. Saturn's radio emissions vary in intensity in patterns that match the rotation of the planet, providing one of the most accurate ways to measure Saturn's rotation period. The rotation rate of Saturn is actually somewhat uncertain. Different parts of Saturn rotate at slightly different rates, the equator slightly faster than the poles. Internal rotation rates inferred from the magnetic field vary between different measurements. The exact length of a Saturnian day is therefore known only to within a few minutes, despite extensive study. Saturn's magnetic field also creates ring currents, bands of charged particles that circulate around the planet at specific magnetic latitudes. These ring currents store enormous amounts of energy and contribute to the overall structure of the magnetosphere. They are similar to the ring currents around Earth that have been studied for decades, but on a much larger scale. Tonight, Saturn's vast magnetic field continues to envelop the planet and its moons. Charged particles spiral along magnetic field lines. Auroras glow softly at the poles. The solar wind shapes the magnetosphere on the sunward side. The long magnetic tail stretches into space behind Saturn. The whole system rotates slowly with the planet, exactly as it has for billions of years. Now, gently, we will turn from the magnetic field to the great spacecraft mission that revealed most of what we know about Saturn, Cassini-Huygens, which orbited Saturn for 13 years and transformed our understanding of this distant world. The Cassini-Huygens mission was one of the most successful planetary missions in the history of space exploration. It was a joint project between NASA, the European Space Agency, and the Italian Space Agency. The mission consisted of the main Cassini spacecraft, which orbited Saturn, and the smaller Huygens probe, which descended to the surface of Titan. Cassini launched from Earth in October of 1997. The spacecraft took nearly 7 years to reach Saturn, traveling via gravity assists from Venus, Earth, and Jupiter. Each gravity assist used the gravitational pull of a planet to speed up and redirect the spacecraft toward its ultimate destination. The complex trajectory was a triumph of orbital mechanics. Cassini arrived at Saturn in July of 2004. The arrival was carefully timed to allow the spacecraft to be captured into orbit by Saturn's gravity. The mission team needed to execute a precise sequence of engine burns to slow Cassini down enough to be captured. Any error could have sent the spacecraft past Saturn and out into deep space. The Cassini orbiter carried 12 scientific instruments designed to study Saturn, its rings, its moons, and its magnetosphere. Imaging cameras took photographs across many wavelengths of light. Spectrometers analyzed the composition of materials. Radio instruments studied the magnetic field and atmosphere. Mass spectrometers sampled gases. Each instrument contributed to a different aspect of understanding the Saturn system. The Huygens probe separated from Cassini in December 2004 and began its descent to Titan in January 2005. The descent took about 2.5 hours. Huygens parachuted gently through Titan's thick atmosphere, recording images and data the whole way. It landed safely on the surface, becoming the first spacecraft ever to land on a moon other than Earth's own moon. Huygens transmitted data from Titan's surface for about 90 minutes before its batteries failed, and the freezing temperatures stopped its electronics. In those 90 minutes, the probe captured the first and only direct images of Titan's surface, recorded measurements of the local environment, and provided crucial data about the moon. The mission was an extraordinary success. Cassini's original mission was planned for 4 years, but it was so successful that the mission was extended twice. The first extension, called Equinox Mission, ran from 2008 to 2010. The second extension, called Solstice Mission, ran from 2010 to 2017. In total, Cassini orbited Saturn for 13 years. During its 13 years at Saturn, Cassini completed nearly 300 orbits of the planet. It made detailed close passes by all of Saturn's major moons. It discovered the plumes of Enceladus, mapped the surface of Titan in great detail, found new small moons within the rings, observed the hexagonal storm, watched the Great White Storm of 2010, and accomplished many other scientific firsts. In its final months, Cassini executed a series of bold maneuvers called the Grand Finale. The spacecraft repeatedly threaded between Saturn and the inner edge of the ring system, passing through a gap less than 2,000 kilometers wide. Each pass was at high speed, exposing the spacecraft to potentially dangerous ring particles. But each pass also returned unprecedented data about Saturn's gravity, magnetic field, and inner ring structure. On the 15th of September 2017, Cassini ended its mission by deliberately diving into Saturn's atmosphere. The mission team made this decision to protect the moons of Saturn, especially the potentially habitable Enceladus and Titan, from any possible biological contamination from the spacecraft. As Cassini fell, it transmitted data until the moment it disintegrated. The final signals from Cassini took 83 minutes to travel from Saturn back to Earth at the speed of light. By the time the last transmissions were received, the spacecraft had already been destroyed for over an hour. The mission team gathered to watch the signal end, a moment of both celebration and quiet farewell to a spacecraft that had served for nearly 20 years. The data returned by Cassini-Huygens fills enormous archives. Scientists are still actively analyzing the imagery, the spectroscopic data, the gravitational measurements, and the magnetic field observations. Many years after the mission ended, new discoveries continue to be made by careful study of what Cassini collected. The mission's scientific legacy will continue for decades. Cassini-Huygens transformed our understanding of Saturn from a distant, beautiful curiosity into a complex, dynamic system. Before the mission, we knew Saturn had rings, moons, and an interesting atmosphere. After the mission, we knew about the hexagonal storm, the geysers of Enceladus, the lakes of Titan, the dynamics of the rings, and dozens of other details that revolutionized planetary science. The mission also represented a triumph of international cooperation. American, European, and Italian engineers and scientists worked together for decades to design, build, launch, operate, and analyze the mission. The success of Cassini-Huygens stands as a model for how complex space missions can be accomplished when nations work together toward a common goal. Future missions to Saturn are being planned. The Dragonfly mission will fly through Titan's atmosphere starting in 2034. Several proposed missions could orbit Enceladus and search for life in its plumes. Other concepts involve sample return from Titan's lakes or detailed studies of Saturn's atmosphere. Each new mission builds on what Cassini taught us. Tonight, the remains of Cassini are part of Saturn itself. The spacecraft's atoms, vaporized during its final dive, mingle with Saturn's atmospheric gases. The greatest spacecraft ever sent to Saturn became, in its final moments, a small part of Saturn forever. The mission ended, but Cassini's discoveries continue to illuminate humanity's understanding of this distant, beautiful world. Now, gently, we will turn from the science and exploration of Saturn to its long human history, the many cultures that observed Saturn through millennia, the mythologies built around its slow movement, and the place this distant planet has held in human imagination. Saturn is one of the 5 planets visible to the unaided human eye. Throughout human history, on every continent, people have looked up at the night sky and seen Saturn, a steady, soft yellow point of light moving slowly against the background of the stars. Saturn has been observed by humans for as long as humans have looked at the sky. To ancient observers, Saturn was distinctive for its slow movement. Of the 5 visible planets, Saturn moves most slowly across the sky. A complete journey through the constellations of the zodiac takes Saturn nearly 30 years, about a human generation. This slow pace gave Saturn a reputation for patience, endurance, and the passage of time. In ancient Mesopotamia, Saturn was associated with the god Ninurta, a deity of agriculture, harvest, and time. Babylonian astronomers working more than 2,000 years ago made some of the earliest careful records of Saturn's motion. They tracked the planet's position over decades, building tables that could predict future positions. In ancient Greece, Saturn was associated with Cronus, the father of Zeus and ruler of the Titans before the Olympian gods. Cronus was a god of agriculture, harvest, and time. The Greek word for time, chronos, comes from the same root as his name. The slow movement of Saturn through the sky was seen as a reflection of the slow passage of time itself. The Romans inherited the Greek mythology, but renamed Cronus as Saturn. Saturn was the god of agriculture, the harvest, and the original golden age of humanity. The Roman festival of Saturnalia, held in mid-December, was a time of feasting, gift-giving, and the temporary reversal of social roles. The festival eventually influenced the modern celebration of Christmas. In English, Saturn gives its name to Saturday, the seventh day of the week. The 7-day week comes from the ancient association of each day with one of the 7 classical planets, including the Sun and the Moon. The order of the planets was based on their apparent speed across the sky, with Saturn being the slowest and therefore associated with the outermost ancient sphere. In ancient India, Saturn was called Shani. Shani was considered both feared and respected as a powerful deity who could bring difficulties but also brought wisdom and discipline. The astrological tradition of Indian culture has had a strong focus on Saturn's influence, considering the planet's movements crucial to predicting both individual and collective futures. In China, Saturn was traditionally called the Earth Star or sometimes the Filling Star. In traditional Chinese cosmology, Saturn was associated with the element of Earth and with the central position among the visible planets. The careful observations of Saturn by Chinese astronomers over many centuries contributed important early data to the understanding of planetary motion. Galileo Galilei was the first person to observe Saturn through a telescope in 1610. His telescope was too small to clearly show the rings, but he could see that Saturn was not simply a round disk like other planets. The strange shapes around Saturn puzzled him. He famously described Saturn as a planet with handles, or as if Saturn had 2 large companions on either side. It was Cassini-Huygens in 1659 who finally correctly identified Saturn's strange appearance. Using a better telescope, Huygens recognized that the apparent handles were actually a flat ring system surrounding the planet. His insight transformed Saturn from a strange triple object into the first known planet with a ring system. In 1979, the Pioneer 11 spacecraft became the first human probe to visit Saturn closely. Pioneer 11 took the first close-up photographs of Saturn and its rings. The mission revealed new details about the ring structure and provided the first direct measurements of Saturn's magnetic field. It opened the era of detailed spacecraft exploration of Saturn. Saturn appears prominently in literature, art, and music throughout history. The astronomer William Herschel composed musical pieces inspired by the planets. The English composer Gustav Holst wrote The Planets, a famous orchestral suite that includes Saturn, the bringer of old age, a movement that captures the slow, stately character of the planet through music. In modern times, Saturn has remained a source of fascination and inspiration. Photographs of Saturn from the Hubble Space Telescope and from spacecraft like Voyager and Cassini have appeared on book covers, in films, on posters, and in countless other media. The image of a ringed planet has become iconic, often used as shorthand for the idea of any planet at all. From any quiet, dark sky, on a clear night when Saturn is visible, the planet can still be seen as it has always been seen, a soft yellow point of steady light. Through binoculars, the rings become visible. Through a backyard telescope, the rings are clearly defined and the planet itself shows a small bright disk. The view today is essentially the same as it was for Galileo or Huygens. Throughout all the millennia that humans have watched Saturn, the planet itself has been doing what it does tonight. The clouds drift, the rings turn, the moons follow their orbits, the hexagonal storm rotates at the North Pole. The plumes of Enceladus continue their patient outpouring. Saturn pays no attention to anyone who watches it. And yet somehow, through all the looking and all the thinking and all the studying that humans have done, Saturn has helped to shape human understanding of the universe. From the slow, patient passage of time to the structure of the solar system to the possibilities of life on alien moons, Saturn has been a teacher. Quiet, distant, and patient, Saturn has revealed many things to those willing to look carefully. Tonight, somewhere in the night sky, Saturn shines on. Its slow movement continues. Its rings reflect the distant sunlight back into space. Its moons trace their long orbital paths, and somewhere in the cosmic dark beyond the spacecraft, Cassini has become one with the planet it once orbited. All is calm, all is patient, all is exactly as it should be. Thank you for trusting your night to this slow voice. The Circadian Institute exists because there is a need in the late hours for stories that do not demand anything. Subscribing keeps that need answered. Each week, a new slow journey through the cosmic world of Saturn and its rings made for sleep. Good night. Let yourself rest now. Saturn is still rotating quietly in its orbit, 800 million miles from the Sun tonight. The vast ring system is still slowly turning, its countless ice particles tracing their patient paths through the deep cold of space. Titan is still circling Saturn through the long cosmic night, exactly as it has for billions of years. The world will keep going, with or without your watching. You can let go. Good night from the Circadian Institute. And with that, we bring tonight's quiet journey through the world of Saturn to a soft close. The pale golden gas giant is still rotating. The rings are still slowly turning. The moons are still tracing their patient orbits through the cosmic dark. They will all continue without us. Sleep softly tonight.